Today, we're going to talk about Einstein, but maybe not the Einstein you think you know. We're going to unlock a side of his genius that goes way beyond that one famous equation and is actually shaping the technology we're all using right now.
So when you think of Albert Einstein, what's the very first thing that pops into your head? I bet for most of us, it's one single, almost legendary equation. Yeah, that one. Probably the most famous equation on the planet. I mean, it completely changed how we understand energy, matter, the whole universe. It's got to be the champion, right? Or maybe not.
Because while E equals mc squared gets all the glory, some of Einstein's other work, stuff he did in the exact same miracle year of 1905, arguably had an even bigger and more immediate impact on how we see reality. And that work, it's still at the heart of the tech you use every single day. And it all starts with something we totally take for granted today, atoms. You know, back in the early 1900s, the whole idea of atoms was still a huge debate. A lot of serious scientists thought they were just a handy little fiction. But Einstein, he helped make them real. And that was some giant machine, but by just watching a very, very tiny dance.
He zeroed in on this thing called Brownian motion. You've definitely seen this. It's that weird, jittery way dust seems to dart around in a sunbeam. For years, scientists were stumped. What invisible force was nudging these tiny particles all over the place?
And this, right here, is the core of his genius in this case. He didn't come up with a direct mathematical proof, not in the way you'd prove a geometry theorem. Nope. He just built this incredibly strong case based on, well, circumstantial evidence. He basically said, hey, let's just assume for a second that molecules are real, and let's see where that takes us. His logic was just beautifully simple. First, he said, let's guess that a fluid, like water, isn't some smooth, continuous thing, but it's actually made of zillions of tiny, constantly moving molecules. Okay, step two, he predicted that these invisible molecules must be constantly smacking into any larger particles, like grains of pollen. And three, he pointed out that this is exactly what we see, that random jittery dance of Brownian motion. It was the smoking gun. The jittering wasn't just noise. It was the echo of an entire invisible world of atoms.
So, boom, Einstein helps prove atoms are real, but he was just getting started. Next, he basically co-authored the fundamental rulebook for how these new, real atoms interact with the universe, especially with light and energy.
The best way to think about it is like a cosmic dress code. See, an atom can't just absorb or spit out any old random amount of energy. No way. There are super strict rules. They're called selection rules that say exactly what can happen. It's kind of like a bouncer at a club for photons. Only very specific energy packets get on the list to go in or out.
Okay, deep breath. We are not going to try and solve the math on screen, I promise. But just take a look at it. This is from a foundational textbook on this stuff. These are the Einstein coefficients, and they are the mathematical guts of everything from lasers to LEDs. This is that deep, fundamental work that literally wrote the quantum rulebook. And this wasn't just abstract theory, scribbles on a blackboard. Decades later, clever experiments like this one in 1936 actually proved these rules were real. This amazing setup with suspended plates and polarized light was able to physically measure the torque, or the spin, of a photon, which confirmed one of the key predictions right out of Einstein's cosmic rulebook.
All right, let's jump forward about a century. How does all this 100-year-old physics actually show up in our world today? Well, you might literally be holding it in your hand. It's inside our batteries. So, building on those same ideas from his work on Brownian motion, scientists later derived what's called the Nernst-Einstein relation, and it's a brilliant piece of insight. It turns out that the same random thermal jiggling that pushes dust around is directly connected to how easily you can push an ion through a material with an electric field. It's this beautiful, elegant link between two super important things for batteries: how easily ions move when you want them to, and how much they just spread out on their own.
So why does that matter?
Well, because measuring both of those things separately is really, really hard and takes a ton of time. For decades, this equation has been an absolutely essential shortcut for scientists. It lets them get a pretty good estimate of one value if they can just measure the other. And that's a huge deal, especially now in the race to build better, safer solid-state batteries. But, and you knew a but was coming, right? This is where our story takes a really interesting turn. What happens when you take a rule book that's 100 years old and try to use it in a brand new place? Well, sometimes the rules break. You see, the Nernst-Einstein relation was built on one really important assumption, one that goes all the way back to Brownian motion. It assumes that the particles, in this case ions, are moving through a fluid, something viscous, like a liquid or a gas, where the main thing they're fighting against is drag.
So in a traditional battery with a liquid electrolyte, the ions are kind of like a swimmer moving through honey. The physics of that smooth, viscous flow works, and Einstein's relation holds up beautifully. But a lot of these new solid-state materials are more like a ceramic plate. They're brittle. Ions don't flow through them. They have to hopscotch their way through a rigid structure that can crack and fracture. The physics of it is just a completely different ballgame.
And that's exactly why this classic model is starting to hit a wall. These new materials, they're not viscous. They're rigid. They crack. They don't flow. And when scientists do the really hard work of measuring both properties directly, the numbers just don't line up with what the Nernst-Einstein equation predicts. That handy little shortcut, it doesn't always lead to the right place anymore.
So, what does all this mean? Was Einstein wrong? No, not at all. It just means his legacy isn't some collection of unbreakable final commandments from on high. It's a foundational toolkit that we are still using, still testing, and still learning the absolute limits of. This quote just hits the nail on the head. Science isn't really about finding final absolute truths. It's about building better and better models to describe the world we see. Einstein's model for how things move and diffuse was revolutionary, and it's still incredibly useful. But as we push into crazy new materials, we're finding the edges of that model and realizing, okay, time to build something new.
When you step back and look at it, from the dance of atoms to the rules of light, all the way to the batteries of tomorrow, Einstein's other ideas gave us the very first coherent rule book for the atomic world. It was so powerful, so effective, that we're only just now discovering the specific places where we need to write new chapters. And that leaves us with a pretty cool question. If he wrote that first rule book, what new rules are we going to have to write for the next one?